Hello, YouTube! Today is probably going to be a two-parter, just as a heads up, where today we're going to talk about how you do it, and then on the next one we'll do probably a bunch of just like follow-up examples. We'll see, though. So today we're actually going to take all the stuff we've talked about so far with position and velocity graphs and add in what happens when there's pretty significant acceleration. And that'll be talking about what the position graphs look like when there's pretty significant acceleration and what the velocity graphs look like, and then how you can use acceleration graphs within that. So the big one is if you can translate between acceleration and velocity graphs, which is important because you hopefully can already go from velocity to position, then we can get between the graphs of all three of our vocab words, and combining that with our ability to model things going at a constant velocity, we've got a decent understanding of how stuff moves, at least in a conceptual way. So in particular for this one, as long as you're able to find the slope of a velocity graph and know what that represents, as well as finding the area of an acceleration graph and knowing what that represents, and then using those to draw the other ones. So acceleration graphs, and we're only going to deal with constant acceleration graphs in this class, are kind of like velocity graphs, but it's like one extra layer of it being a rate of something. So because acceleration is the rate of change of velocity, what you see when you're looking at an acceleration graph isn't the way that it's currently moving. What you're seeing is the way that it's trying to move more in. So if the acceleration graph is positive, aka above the line, which would be anything up here, like in this section, what that tells you is that your velocity is getting more positive. In this case, because it's plus 3, that means that every second you wait, your velocity needs to go up by 3. Now, if you remember, that doesn't actually mean that you're speeding up. Because if your velocity is currently, let's say, minus 15 when you start doing that, you would go from minus 15 to minus 12, then to minus 9, and then from there to minus 6. And throughout this process, we're moving backwards progressively slower over time. So the big one is that if you have that positive acceleration, if your velocity is positive, it will mean you're speeding up because it's getting more positive, meaning more big. But if your velocity is negative, that means you will be slowing down because your velocity is getting more negative and slower as a result. If you have negative acceleration, the exact opposite is true, where if you're moving backwards, it means you're getting faster. If you're moving forwards, it means you're getting slower. Zero acceleration does not necessarily mean that you are stopped. It means that your velocity is not changing. Remember, acceleration is the way your velocity is changing. So no acceleration here means constant, the same velocity. If you remember back to when we were talking about velocity graphs, we talked about how the slope of the velocity graph is the acceleration. Well, you can also think of it as saying that the acceleration graph is going to be the slope of any velocity graph you have. So for this section, the acceleration being positive 3 just means that you know about the slope of the velocity graph. This is a little weird because like it's dependent on v, so you don't actually know what the object is doing at all, but you will know, and this is something that I don't think I've talked about yet, what the object feels like it's doing. So something that's a little bit weird is that you as a person can't feel speed. You can feel things hitting you if they're going quickly, so like if you get hit by the wind a lot, and the wind is going incredibly quickly, you will feel that, but you won't feel the fact that you're moving quickly. If you've ever been in an airplane, it probably doesn't feel overly different from being in a car, and being in a car going at 80 doesn't feel overly different from being in a car going at 20 unless you feel the vibration of the car from the wind hitting it. And the reason for this is that what you're actually feeling when you feel motion isn't the motion, you're feeling the acceleration. So if you think about being in a car when it slams on the brakes, you'll feel yourself moving forward. Well, that's not actually you feeling yourself moving forward. What you're feeling there is your organs pushing against the inside of your body and then them getting pushed backwards, meaning you're accelerating backwards. So weirdly enough, if you're thinking about the way that it feels like something is happening, there's a solid chance that what you're actually thinking about is an acceleration happening in the opposite direction as the way you feel like you're moving. And that's what these graphs are showing you. is that if it's got a positive velocity, it means that you will feel yourself getting pushed backwards, which is, or like you'll yeah, that's typically the way it winds up manifesting. So, again, these get even one more step in counterintuitive, because the velocity graphs are showing you what it looks like the object's doing, but not what the object is actually like is, or where the object is. And acceleration graphs don't even show you what it looks like it's doing. It shows you what it would feel like it was doing if you were in it, sort of. So this is sort of showing examples of all of how these things can match up with constant acceleration. So if you have an object that has an acceleration graph like this one, what's relevant about this is that it's a negative acceleration and it's constant, which means that the slope of our velocity graph will need to be staying the same as we go. So if we come over from 2 to 4 seconds, if the velocity starts positive, it'll have a negative slope that remains the same until it hits 0, in which case, if we look over here, we still have the same acceleration. So our acceleration hasn't changed, but because we stopped and turned around and we're getting more negative as we go, we've actually completely changed what the object is doing, even though its acceleration is identical. We start out being pretty high up, meaning fast. We end up at 4 seconds at 0, meaning slow. So during this section, because we're above the line and have a positive velocity, here it's +4, we start at +4 and we gradually get smaller until we get to 0, meaning the whole time we're moving forward. So this is showing an object that is moving forward and slowing down, which requires a negative acceleration. This part is showing an object that is moving backwards and speeding up, because the whole time the object is moving, the velocity is negative. And the whole time that it's there, it's getting progressively more negative. So this one is moving backwards and speeding up until we get to 7 seconds. Now at this point, our velocity is getting more this is flipped. This should be that the velocity is getting more negative. This one is that the velocity is getting more positive. Because our acceleration is positive, our velocity is getting more positive here. So we need to go from where we were before with our velocity and get more positive until we cross the line. And when we do that in this section, our acceleration hasn't changed, but because we went from slowing down until we stopped, after we stopped, if the acceleration stays positive, we'll keep getting more positive, meaning we'll go forward and speed up. And what that looks like when we come over to the position graph is that we start out very fast, meaning we start out steep. If you look at this line, it's going up by, let me get a different color. If you look at this line, it's going up by 2, over by 1-ish. Whereas when we get here, we're not even going up by a full 1 by the time we get to the top. It starts out very steep, it ends up very shallow. So this one is slowing down, just like the velocity graph says we should be. But because the velocity graph is positive the entire time, our position graph needs to be getting more positive. We need to be moving forward. So this is what it looks like to be moving forward and slowing down. Over here, we're moving backwards and speeding up. We're starting out very flat, we're ending up very steep, so we start out slow, we end up fast. The whole time it's going down on the graph, which means the object is moving backwards on a position graph, which corresponds with this section. For this section, we start out fast, so start out fast, steep. We end up slow, and the entire time the graph is negative, which means of velocity. And because we have a negative velocity, we need to be moving backwards, so the position graph needs to be going down. So we need to start out steep, end up slow, and move down the whole time. Oftentimes what I like to do for these when I have to draw them is make the first line based on the fact that I know that it should be slow. Now I know it should be fast, and the entire time it's positive, it's above the axis. The velocity is above the axis. And so my position graph will need to be steep and somewhere higher up. And then I can take those two lines of flat and steep and then connect them, and that gives me roughly the shape that I'm supposed to have. So because it matters when things wind up crossing the line, it'll actually really matter where your velocity graph starts to determine what the object is actually doing based on the acceleration graph. And it is really hard to tell what's happening based on just an acceleration graph. You'll need something else as well. Oftentimes just someone telling you where to start it. Unless I tell you otherwise, assume that it starts out at rest, meaning it starts out with the velocity being 0. But there will be problems where that's not the case. So taking it in a little bit of a less chaotic way, just as far as how to match all these together, if you see something like this, this is a position graph that is moving forward with a constant velocity. There is no slope, there's no curve, it's just very straight, which means that the slope is staying the same the whole time. Our velocity is positive and staying the same the whole time. Our acceleration for this has to be 0 though, because constant velocity means it's not accelerating. Same thing here, except because the velocity is negative, our position is going down the whole time, even though it's got the same acceleration graph. If we look at other options for constant velocity, really the only other one is if we're not moving at all, in which case our velocity is constantly 0, meaning the whole thing is at rest. So our position stays whatever number it was originally the whole time. Your acceleration will also be 0 in that case. If we start getting into places where we are actually accelerating, what it'll look like is we've got something like this, where our acceleration is the same the whole time, and in this case it's positive. If we start out with a velocity of 0 and we have a positive acceleration, we'll move forward and speed up. So we need to start out being very flat, going very slow, end up very steep, going very fast, and the entire time the graph needs to go up. If we have something like this, where the acceleration is negative, but we start out moving forward, our velocity needs to get more negative as we go. So we'll get progressively closer to 0. 0 is really slow, so at the end we'll be really slow, and at the beginning we're really fast because this is a big number. So when we look at our position graph, it starts out very steep, or because the velocity is big, and it ends up very flat because the velocity is small, but the whole time the velocity is above the line. So because of that, we need to be moving forward, and it'll look something like this. If our acceleration is positive, but our velocity starts out at negative, we'll get a similar thing where the end is very flat and the beginning is very steep. But because the velocity is negative the whole time, we're going down on our position graph as time goes on. And our last option would be something like this, where we've got a very flat beginning, a very steep end, meaning we start slow, we end fast, and we're just connecting the two going down the whole time because this is negative the entire time. Again, when I'm saying the velocity is negative, I'm not saying that the velocity graph is going down. That means that it is accelerating backwards. The velocity being negative is a function of it being below the line, meaning if I picked a random point here, this would be something like -3, where it's an actual negative number for the velocity. Before we do this, I actually want to we'll leave that for part 2. If you're having trouble thinking about how you would translate between different graphs, we'll do a bunch of examples for that, explain what different shapes look like on position graphs, and that'll be part 2. All right, so what if we have an acceleration graph and we actually want to be really careful about our velocity graph the same way that we can be careful about a position graph using a velocity graph? Well, the process is the exact same. You won't ever get triangles, which makes your life a lot easier. Because velocity is the thing that acceleration causes a change in, the area of an acceleration graph gives the amount of change that that acceleration did to the velocity. So the area of an acceleration graph is going to give you the change in velocity for that graph. So if we look at this first section, the base is 4, the height is 4, and so our area winds up being -16. So what that means is that from 0 seconds to 4 seconds, whatever our velocity used to be, it got lower by 16. And not necessarily slower by 16, it just got 16 more backwards. In the next 2 seconds, it gets 4 more backwards because base of 2, height of -2. This next one's above the line, so we wind up with a positive acceleration. So for this one, we've got a height of 8 and a base of, a height of 2 and a base of 4, and so our area winds up being +8. For this section, it's on the line, so whatever the velocity was at this point, it would just stay cruising at that velocity for that entire time. One quick other thing is that you can find your total change in velocity this way, and that'll let you figure out your average acceleration. That's more of a thing for Physics C than it is for AP1, but in theory that does exist, where your average acceleration is going to be your change divided by time, just like how your average position was your, or sorry, average velocity was your position divided by time. So, again, I think part 2 we'll do some more in-depth examples on how to draw the graphs. But for now, I think this is a good place to leave off. So thanks and goodbye.